speaking of stuff that's good for you, let's talk about radiation. Like that. So we'll get to go see some radioactive stuff up in lab today and play with some radioactive. We talked about three of the forms of radiation: alpha particle emissions, beta emissions, and gamma emissions. We'll look at all those different kinds of emitters up in lab. So the things we want to talk about now, first, how we measure radiation and radioactivity. We want to look at that, and we want to look at something called half-life, which is a measure of how long radiation will stay around. All right. So we looked at these different ways that these things decay from metastable states into whatever they decay into. And we talked a little bit about how they're used in medicine and some other things like that. So now we're going to look at how we actually measure this. So we want to measure radiation in two ways. We want to measure how much radiation is coming out of something. So we want a measurement of like emitted radiation. And then we want to know how much radiation is getting into something else. So how much radiation is being absorbed by your body, say, or how much radiation you're exposed to. So we're going to look at two sides of that. The first side is the emission of radiation. The emission of radiation is often measured in curies, which the abbreviation is CI. So just like any other units, you can have microcuries or millicuries. Curie is actually a pretty substantial amount of radiation. And it's defined as the disintegrations per second of 1 gram of the element radium. And that number is actually 3.7 times 10 to the 10th. So a big number. So in 1 second, 1 gram of radium will give off 3.7 times 10 to the 10th particles, or it'll do that many disintegrations. Each disintegration is like one reaction for one atom that we looked at last time. And that's an alpha emitter, so that's one alpha particle emitted. All right, so another, a more general unit then is called the Becquerel. Did you spell that right? Yeah. Or the BQ, and that's a much smaller unit. That's just disintegrations per second. So you would say that a gram of radium emits 3.7 times 10 to the 10th becquerels of radiation. Smaller unit. That's often useful, as you'll see, like upstairs when we look at actual radioactive stuff. We usually don't have so much that it's emitting curies of radiation. It's usually like millicuries or microcuries. So it makes more sense to have a smaller unit like that. So those are the emission units, and then the exposure units. The basic unit is called the rad, which stands for radiation absorbed dose, RAD, radiation absorbed dose. And that is the amount of radiation absorbed by 1 gram of whatever. So a gram of skin tissue, a gram of person, a gram of rock, a gram of wood, whatever. The amount of radiation absorbed by a gram of something is called a rad. And that was the major measure for a while. Now that's been replaced with something called a rem, and this is the more important measure now. The rem is actually just like a rad, but with a correction factor. So this stands for radiation equivalent in humans. And it just is the rads times a particular factor depending on the type of radiation. And we don't have to really go into the specific calculations of that, but it's just recognizing that some types of radiation do more damage to human tissue than other types. Like alpha particles, for instance, are much more massive and highly charged. So an alpha particle hitting you is, even though they're blocked more easily, but if they get inside and they are hitting your tissues, that's going to cause a lot more damage than, say, a gamma ray, which is mostly just passing through. So this attempts to kind of equalize the fact that 100 rads of gamma rays is different from 100 rads of alpha rays, and just say 100 rems of either should be the same. So it's a way to standardize that dose. So if you are if you're a technician working in a radiologic technician, let's say, working with X-rays, or you're working in nuclear medicine, you're working with some of these radioactive isotopes and caring for people, you'll be monitored. Your radiation dose will be monitored in REMs by a couple of ways. Usually there's some sort of a badge that you can wear that you always wear while you're doing your work. And so the assumption is if you get exposed to X-rays, that badge is also being exposed, and then it's measured every few weeks or something to see if it's been exposed to too much radiation. It also depends on what you're working with. Like when I used to work with a lot of X-ray instruments, I would wear this ring. It's like a little plastic ring that detected X-rays or was damaged by X-rays. And so when you're working with stuff, if the X-rays happen to be on and hit your hand, then when you sent that in for analysis, you'd know that you were being exposed, that you had been exposed to X amount of radiation. So just to give some numbers on where you want to be or not be with this stuff. So make another page here so a little more room. Oops. The lethal dose of radiation, the LD50, which is the dose at which 50% of a sample of people would die, is 500 rem. So 500 rems of radiation, that's what's going to just kill you instantly. Now, this doesn't mean give you cancer and you'll die eventually. This means that's what you can't, you can't process that. It will just destroy too much tissue. The average that we're all exposed to is around 360 millirem per year. So, well, remember that's millirem. So 500 rem is 500,000 millirem. And average for people is about 360 millirem per year. And that's coming from all the sources we talked about, coming from rocks, coming from space. If you fly, that average is going to go up a little bit. If you get a lot of X-rays, things like thoracic CT scans tend to give you a higher incidence of that. So that's something you might be monitored for. Make sure you're not getting too many of those within a year. So you don't want that level to get too high. The upper limit set by OSHA you shouldn't get a dose of more than 25 rem ever. Remember, that's rem, not millirem. So that's 25,000 rem. You should never get that much at once. That's the threshold at which they say, okay, you're going to start having some real problems from that. And then if you're working with radiation regularly, you shouldn't get more than 5 in a year. So if you're anything above that, and these limits are set a little low also, right, to be safe. So you could probably exceed it a little bit, but it's getting well above those that you're going to start potentially having a greater incidence of various problems from the radiation.
Give us something to compare it to, say, like an accident at the nuclear facility or a bomb or something like that. Like, how much does that entail, and what does it mean if it lets off a large amount? Why does distance, it dissipates, and that's why distance would work in your favor?
It's not so much that it dissipates, but that it transfers the energy to molecules in the air. The molecules in the air will absorb that radiation. Distance as well, just because energy will go down, but primarily it's the air molecules blocking the particles. So the energy will be transferred to the air. The energy from the radioactive particles transferred to the air particle, whatever it is, an oxygen molecule or a water molecule or something like that in the air. And so now you no longer have this energetic particle flying through the air.
So is that why something like, that's why they would have nuclear fallout, because the energy is never going to go away. So now that air molecule or that water molecule is now radioactive, and
depending on how much energy you start with. So if you think about something like a nuclear bomb, this nuclear bomb explodes at a particular site. Everything in a radius, I don't know the numbers there, but anything in some kind of radius is just gone because of heat or because of, and then, so everything in a relatively small radius is gone just because of the heat. The energy that's put out just melts everything. And then it vaporizes everything, actually, beyond melts it. Then beyond that, you've got radiation, you got like the 500 millirem or 500 rems of radiation poisoning that's going to kill a lot of people fairly quickly. But then you also have all the energy that's transferred into, like you said, the ground, the soil, and the fission products. We'll talk about the nuclear fission reaction of this thing, these atoms breaking up. And a lot of those products will stay radioactive and stay bombarding other stuff and whatever for a far amount of time. So that's what they talk about by nuclear fallout is, all the other stuff that's getting the energy transferred to it and then becoming radioactive because of it.
Just had news that I reached California, the radiation. It reached the Pacific Oregon, all the way across the Pacific on the shores of California. So it looks like it's because it's been 2 years too, so it's a while.
So how much does something like that emit? Like,
I'm trying to find a number here. It's a good question, yeah.
Or
I think just crashed.
Problem, an accident at a nuclear facility, what could that?
I would imagine it depends on the scale of it, but the scale of the accident, how much actually gets out versus how much is contained in the fuel, and how much fuel was actually involved in that reaction. Yeah. So I don't know those numbers. I mean, certainly way more than 500 rems. I don't know. We'll have to look that up and see. There's gonna be a lot of downtime during lab today, so maybe we can do that. I'm trying to find. I know the book has some numbers in here. It's loading very slowly for me right now. All right. Well, we got a little bit of time. Let's move on to our last bit of stuff here. And that's Halflife. You know what Halflife is? Thanks.
Yes, that's
helpful.
PC game, man. I used to
It's
say
how
that.
long something sticks around, right?
Yeah, it has to do with how long something sticks around. So for a video game, it's what, like a year, and then a new one comes out, and then.
Like for medications, the half-life is how long it stays in your system, right?
Right. So half-life can be applied to a lot of things, not just nuclear radiation, like medicine. Half-life is actually how long before half of something is gone. So the half-life we can define as the amount of time it takes for half of half of something to, I'll just say go away because that's more general. We don't actually mean that something ceases to exist, but it transfers to another form. So for a radioisotope, a radioactive isotope, after half of it has decayed and become something else. Maybe decay is a better word here, in our case. For medicine, it's how long it takes before half of it is metabolized and turned into something else in your body. Right. So it's kind of a general term. The reason we look at how much time before half goes away, rather than just saying how long until all of it goes away, is because the way that these things work, they actually decay in this fashion, which is called exponential decay, meaning they kind of cut in half and cut in half and cut in half. So it actually takes a lot longer for the second half than the first half to totally decay. So it's going half by half by half. And so if we're waiting if we're expressing a number in terms of how long the whole thing takes to decay, it's really not a good picture of how fast it's decaying because of that trend. So let's talk about what that means and what we mean by that. Let's say we have a radioactive isotope of iridium, iridium 192. Iridium 192 has a half-life of 74 days. The way that that's written is we'd say the T1/2, which is the half-life, that's a symbol for half-life, is 74 days. And you'll see on the radioisotopes upstairs in lab, this will be listed for each one. It'll tell you the half-life for each one. So iridium has a half-life of 74 days. So that means that, let's say we had 10 grams of it. In 74 days, we'd have 5 grams of it. In another 74 days, so now 148 days total, we'd have 2.5 grams of it. In another 74 days, we'd have 1.25 grams of it, and so on. So it keeps cutting in half. Now, it's not like it all sticks around and then magically at that 74-day point, half of it's gone. It's slowly decaying throughout those 74 days. And in fact, you can use an equation to calculate exactly how much there would be left after, let's say, the 23rd day or something. We're not going to do that in this class, but you can.
That's 1 mole though, right? 1 mole of iridium? Or?
I said 10 grams. 10 grams of iridium, which would be way less than that.
That's like way less, right? Because it's like 1.
Well, it's 192. Right? We're looking at the specific isotope. Did you have a question? Okay. Put your hand up. All right. So after this amount of time, it decays. It also means that the amount of radiation coming off of a particular sample is going to go down over that same amount of time. So if we said that the initial sample of iridium, let's say, had 8 times 10 to, I think this is a problem in the book, 8 times 10 to the 4th becquerels of radiation, that's what was being emitted by this sample of iridium. After 74 days, we'd have half as much radiation coming off of that sample. So this is how half-life is used in things like nuclear medicine. You want this isotope to be around in the body for a certain amount of time to bombard whatever with the radiation for that certain amount of time, but you want to be able to specify this. So we want this total dose over this amount of time, and so we put it in and we measure the half-life and say, okay, that means you need this many grams of this over 7 days or whatever it is.
Where did you get the
I just randomly came up with that number. I think those go together. Yeah. So you'd have some initial thing given. All right. So let's see how we might answer a question about this. Let's look at a radioisotope of phosphorus that's used in medicine. Phosphorus 32 has a half-life of 14.3 days. So what I might ask is, how long until 1 milligram remains of an 8 milligram sample? So we have 8 milligrams of phosphorus 32. How long until there's only 1 milligram left? What do you think? How do you think you could figure that out? Yeah.
Half of that.
Right. So that's the easiest way to do these problems. If you're not, which we're not going to get into in this class, is just to keep cutting something in half and figure out how many half-lives that is. So we start with 8. After 1 half-life, we go to 4. After 2 half-lives, we go to 2. And after 3 half-lives, we go to 1. So 1 milligram remains after 3 half-lives. So then we say, okay, well, how long is each half-life? 14.3 days. 3 of those, 14.3 times 3, I was going to go 42.9. 42.9 days. So after 42.9 days, 1 milligram will remain of an 8 milligram sample of phosphorus 32. All right. Let's look at it another way. This time we're going to talk about that gamma emitter, technetium-99m. This is the most popular isotope in nuclear medicine. It's used for imaging and all kinds of other stuff. So let's say we start with 80 milligrams. After 24 hours, 5 milligrams remain. Question is, what is the half-life? All right, so I see some people kind of counting it out on their fingers, writing it down. That's fine.
Um,
4.8 hours. Maybe get something different. 6 hours. Let's count it out and see. So we're going to start with 80 milligrams and get to 5 by counting in half. So we go 80, 40, 20, 10, 5. So how many half-lives is that? Yeah, 4. 1, 2, 3, 4 half-lives. So this is saying that in 24 hours, we went through 4 half-lives. So then how long is a half-life? Yeah, so then 1 half-life is 6 hours. By going from 80 to 5, we did 4 half-lives, and we said that those 4 half-lives occurred in 24 hours. So if you have 4 of something in 24 hours, it's got to be 6 hours each. right? Last thing we're going to talk about nuclear fission. This is the reaction that happens in a nuclear power plant or an atomic bomb, splitting the atom. It's another way of looking at this. I'll grab my picture here. So rather than write the reaction down, I'm just going to show you a picture of it from the book. So you take a large nucleus of uranium, uranium-235. And it was discovered that when uranium-235 is bombarded with a neutron, it absorbs that neutron and becomes unstable. But then instead of just emitting that neutron out, it actually breaks in half, or nearly in half, and becomes two different radioactive elements, krypton-91 and barium-142. Also then shoots out 3 more neutrons. So this is what the nuclear equation looks like down here. A neutron plus uranium-235 gives you uranium-236, which then breaks up into this plus 3 neutrons. And the masses all still kind of add up there. But in this case, in addition to all this, you are giving off an enormous amount of energy, incredible amount of energy. The energy density of this stuff is truly remarkable because there's this force that holds the nucleus together that is different from other forces that we know. It's not electrostatic or anything. And by splitting the atom, we've released that energy. So a huge amount of energy comes out, and that's what we get in a nuclear power plant or an atomic bomb. We get a lot of our power here in the Chicago area from nuclear power around Illinois. The other powerful thing about this reaction is it releases 3 more neutrons. So those high energy neutrons can go on to hit more uranium and kind of keep this thing going. And if you see in your book, there's a big picture of kind of a couple steps of the chain reaction. You can see really quickly, it's because each of these can go get another nucleus. Well, now you've got 3 fission reactions happening, and each one of those also gives off 3 more neutrons. So this thing becomes this huge chain reaction. That's why an atomic bomb works. This thing just goes so quickly. In a nuclear power plant, we want to control that. So we have these fuel rods that we can kind of take out of the reaction if we want to stop it, so that it gets them away from the neutrons. And that way we can control the reaction to only release the amount of energy that we want it to release, rather than just let it go unchecked. So that's nuclear fission. And then the counterpart to that is what's called nuclear fusion. In this case, 2 radioactive hydrogen nuclei, hydrogen-3, come together, form a helium atom, and a neutron, and a bunch of energy. Now this reaction is a lot nicer in terms of materials. You don't have this uranium to refine. You actually get a whole lot more energy out of fusion than out of fission. This is the reaction that's happening in the sun and every other star, and creating its energy that way. And it can be self-sustaining as well. The problem with this reaction is that it needs 100 million degrees, not just like a big number, but like literally 100 million degrees Celsius to actually get this thing started. So fusion so far has been impractical from a power standpoint on Earth, because you have to put so much energy in just to get to the temperature that it actually happens, that the energy you get out isn't worth it. So that's why we don't use that. The only time we've done nuclear fusion reactions on Earth, a hydrogen bomb is what this is. In that case, you're actually using a nuclear fission reaction to create the heat to start the fusion reaction, which then goes off and does more. So that has happened. And we've done fusion at some lower temperatures in a lab setting under special circumstances. But this is kind of a almost magical dream of physicists to find a cold fusion.
Until we develop a technology to harness the power of the sun in the future, then that would be awesome.
Right, which we sort of do have the technology to harness the power of the sun. It's just like we have solar panels and stuff.
Yeah, but
It's just not that
not
efficient.
sufficient. It's still weak. I mean,
Yeah.
I mean, we're talking about like real, like lots and lots of power.
Yeah, yeah. All right. So let's head upstairs and we'll look at some isotopes.